The next set of operators are bitwise operators. Python support bitwise operator to perform binary operations on binary code of an integer number. To get the binary code of an integer number, divide the number by 2 till you get the final remainder either 1 or 0. If you are dividing an even number, final remainder would be 0, or if you are dividing an odd number, the final remainder would be 1. Once you reach the final remainder, either 1 or 0, start writing the remainders in reverse order from bottom remainder to the very first or top remainder. That would be the binary code of that particular integer number. And the various bitwise operators supported by Python are binary and the special character used to represent binary AND operator is ampersand binary, or the special character used to represent binary OR operator is pipe binary XOR. Cap is the special character used to represent binary XOR, and we have binary NOT or binary ones complement represent using tilde, and then binary left shift represent using double less than symbol, and finally we have binary right shift represent using double greater than symbol. These are the different bitwise operators supported by Python. Now let's understand more about these operators with some example. In Python, we have a bin function to get the binary code of an integer number. Simply pass the integer value to the bin function. It will return the binary code of a integer value by removing the leading zeros in binary code. So let's say we have bin function. If you want to see the binary code of 5, if you hit enter, it will return 0b101. So here 0b indicates the representation of binary code of 5 in 0 and 1's format. If you want to display binary code in required number of bits by removing 0b and keeping leading zeros, you can get it by using format function. In Python, we have a format function which will allow us to format our string in a different format. Let's say if you wanted to display the binary code, how you can do is format the number you want to convert to binary. Let's say we have 5 here and 0, and then mention how many number of bits you want to display as your binary code. Let's say I want to have it in 6 bits binary code. If I simply give 06b, I'll get the result as 6-bit binary code of integer value 5. That is nothing but 000101. For the same number, if you give 8 here, you'll get the 8-bit binary code of integer value 5, like 00000101. Now let's create two variables a and b and assign values to those variables, and we can see how we can perform bitwise operation on these two variables a and b. Now let's say a equal to 5 and b equal to 2. We have two integer variables created. If you see the type of a variables, both are integer variables. Okay, now get the binary code of a and b in 6-digit binary form. Let's say format a comma 06p. Now if you hit enter, you'll get the 6-digit binary code of a. If you give same format, now if you give b and hit enter, you'll get the 6-digit binary code of b. Okay, now let's perform each and every bitwise operator in between a and b. Okay, the first operator is binary AND operator, and the special character used to represent is ampersand. Now if you give a and b, you'll get the binary result in integer format like 0. So let's use format function as well to understand how the result would be in a binary code. Let's say we have a comma format a comma, I'm giving 06b to get the integer value and the corresponding binary code in 6-digit binary code. Okay, now if I give again b and then here also b, now if you hit enter, you'll get the binary code of b as well as the integer value. Okay, and the first bitwise operator between a and b we can perform in this way: a and b comma format of a and b comma 06p. Okay, if you hit enter now, you'll get the result as 0 comma all zeros. What binary AND operator do is it will compare the bits in both the operands and convert the resultant bit to 1 if and only if both operand bits having 1 as value in the same position. Otherwise, the resultant bit is 0. Now let's compare the bits here. The rightmost bit is the first bit and right but 1 is second bit, and so on it goes like from right to left. Likewise, if you use binary AND operator, the first bit in both the operands having 1, the resultant bit would be 1 in its first position. Here, first bit value in A operand is 1 and the first bit value in B operand is 0. That is why we got the result as 0. Similarly, the second bit operand is 0 and the second bit operand in B is 1. That is why again 0. And the third bit in operand A is 1 and the third bit in operand B is again 0. That is why third bit also 0 here, and rest of the bits all are zeros. That is why all zeros here. So the final bitwise binary AND operator result is all zeros. The binary AND operation on A and B return the binary value as 0 in integer value. The next bitwise operator is binary OR, and the special character used for this operator is pi. Okay, so let's take the same example, the above example. If you replace ampersand with pipe, we will get the binary OR of A and B. Okay, if we hit enter now you see the integer value of A binary OR B is equal to integer value 7 and the binary code is 0001111. It will compare the bits in both the operands and convert the resultant bit to 1 if either the operand bit having 1 as value in the same position, otherwise the resultant bit is 0. Now let's compare the bits here in both A and B operands. In the first bit of A operand is 1 and the first bit of B operand is 0. Because either operand having 1, the resultant would be 1. That is why we got 1 as a resultant bit. And similarly here the second bit is 0 and again second bit in B operand is 1. The resultant bit is 1. And here in third bit is 1 and again here third bit is 0. So we got the final result as 1 and rest of the bits all are 0. So all three zeros came. So finally binary OR of A and B is 00011 as binary value, that is nothing but 7. And the next bitwise operator is binary XOR. Binary XOR, and the special character used to represent this operator is cap. Now let's reset the value of B equal to 3. Okay, now if you perform the binary of B is 3000011. Okay, A cap B comma format A cap B comma 06 bits. Okay, we have the value as 6 and the binary code is 000110. What binary XOR operator do is it will compare the bits in both the operands and convert the resultant bit to 1 if and only if either the operand bit having 1 as a value in the same position, otherwise the resultant bit is 0. Okay, now let's compare these values here again. So if you see the B value is actually 000011 here and we have the A value as 000101. Now if you compare these two, here first bit value in A operand is 1 and first bit value in B operand is 1. So as both the operands having 1 in their first position, the resultant bit is actually 0, because if and only if either bit is 1, the resultant bit will set to 1 in binary XOR operation. So the resultant bit is 0. The second bit in A operand is 0 and the second bit in B operand is 1. That is why we got the result as 1. And even in third bit is actually 1 in A operand and the third bit in B operand is 0. That is why we got the result as 1. And rest of the bits all are 0. So we got all as 0. So the binary XOR of A and B actually 000110 and the corresponding integer value is number 6. Okay, and the next bitwise operator is binary NOT or binary ones complement, and the special character used to represent this operator is tilde. The simple definition is this operator returns a negative value by increasing the value of an operand. Let's understand more about this. Okay, let's say we have A comma format tilde A. I want to have it in 6-bit binary code. If I hit enter, you will get the result as -6. What is actually the A value here is 5. The ones complement will give you the negative value by increasing the value in operand. That is nothing but 6 here. So let's understand more about this. Basically, if you divide an integer number by 2, you will be getting the binary value of that particular integer by writing the remainders from bottom remainder to the top remainder, right? The complement operator inverts the sign of an operand and also flip the bits from ones to zeros, zeros to ones in its binary code. Let's say we have our binary code here, 000101. The complement here, the binary code of 5 is what? We have 000101, right? The complement operator inverts the sign of an operand and also flip the bits from ones to zeros and zeros to ones in its binary code. Complement of 5 is, I'm going to invert 111010. I simply inverted the bits from 0 to 1 and 1 to 0. This is the complement of 5. Okay, and that would be of negative. It's of negative. Okay, and then you will be getting the ones complement by adding 1 to the complement binary code. Let's say if I want to add here 111 0 1 0, if I add 1 to this number plus 1 means it will give you 0 plus 1 1, and we have 1 again here, and we have 0, and we have 1 1 1. Okay, this is the ones complement of binary code 5, which is of this number 111011. If we add another 1 to this binary code, you will get the 2's complement binary code. Basically, in computer memory, the positive integers will save in binary form, but the negative numbers will save in the form of 2's complement binary code. So let's understand with the above example how 5 become minus 6 in binary ones complement. The minus 6 binary code is here. If you see, we have 00110, so means 00110, right? This is the binary code of minus 6. That is nothing but a negative 1. Complement of 6 actually will return 111001. This will be the complement. Just flipping the digits here, 0 to 1, 1 to 0. This will be the complement of minus 6. And here actually earlier minus 6 we are complementing, that is why the return code is positive here. Add plus 1 to this will give you 1 plus 1 0, and that 1 will goes here again, and now the next digit is 0, and again we have triple ones. This will be the ones complement of minus 6, that is 111010. As I mentioned, negative numbers will save in 2's complement in a memory, right? So we need to add one more plus to this particular ones complement. Will give you the 2's complement binary code. That is nothing but 0 plus 1 1, and again 1 there. We have a 0 here, and we have 3 ones. So here if you see, this is a positive value, right? So if you see here, complement of 5 is 111010. Actually what ones complement do, it will give you a negative result by increasing the value in the operand. If you increase minus 6 with 1, the result is 5, right? Minus 6 plus 1 is equal to minus 5. If you compare the bits here, you can see 111011, 111011. Both are matching. Here the final result of 5's ones complement is 111011, and minus 6 2's complement is 111011. Both are same. That's how 5 ones complement is minus 6 and minus 6 ones complement is 5. Basically, complement will change the bits from 0 to 1 and 1 to 0 along with sign. In simple definition, ones complement will give you the negative result by increasing an operand value. So now if you perform ones complement of minus 6, if you give like this, okay, comma, format minus 6, comma, 0, 6b. If you hit enter now, you'll get the result as 5. See here, the result as 5. That is nothing but 000101. And the next bitwise operator is binary left shift. And the special characters are double less than. What binary left shift do is, it will shift the bits in left operand by the number of bits specified in the right operand to the left. A double less than B, comma, format A double less than B, comma, 0, 6B. If I hit enter now, you will get the result as 40, and the binary code is 101000. How it happened? Basically, the simplest way to remember the functionality of binary left shift is, if you are using left shift operator, just add those many number of zeros specified in right operand on complete right side of left operand binary code, and discard those many number of bits on complete left side of left operand. Here if you see, A equal to 5, B equal to 3, and the left operand is A here. So now if you execute again, this is the binary code of left operand, and the bit specified in right operand is 3. Here what we'll do is the 3 bits from right to left. Okay, these 3 bits will be moved from right to left, and zeros will be added and leftmost bits will be discarded. That is the reason we got 101 000 as a result here. The simplest way to remember is just add those many number of zeros on complete right side and discard these zeros will give you the result of A left shift B. Similarly, A right shift B, format of A right shift B, 06B will give you the result as all zeros. What binary right shift do is it will shift the bits in left operand by the number of bits specified in right operand to the right. The bits got moved to right to 3 positions. That is why the rest of the positions has been added with zeros. All the bits from the right got discarded. Okay, here the simplest way to remember the functionality of binary right shift is if you are using right shift operator, just add those many number of zeros specified in right operand on complete left side of left operand and discard those many number of bits on complete right side of left operand. This is all about bitwise operators and how we can use in Python.